Shall we start, Stefano? It's 2:30.
Yes.
Okay, so good afternoon. So next speaker is Professor Stefano Morra from University of Paris 8, and he is going to give a course, short course on completed cohomology for Shimura curves. So the first course, first class, and thank you very much for kindly accepting the invitation. So please, Professor Morra.
Okay, so thank you very much for this invitation. It's a great pleasure and a great honor to give this course. And I feel a little bit intimidated as I see a lot of experts in the field. So this course will be a very gentle introduction to the completed cohomology as introduced by Christophe Breuil and developed fully by Emerton for in the special case of Shimura curves. And here is a bibliography of the material that they will use during this lecture. So, well, there will be a course of, we follow a course of Christophe Breuil, which was given in Orsay a couple of years ago. Then the main reference will be the paper of Emerton, Interpolation of System of Eckler Eigenvalues. And today I will also use this other work of Emerton on local analytic vectors, and the classical reference of Caraiolla is his paper in Compositio 86, the Deligne, the Bourbaki talk, and it will be useful also for today the Schneider-Teitelbaum work on Banach space representation and Iwasawa theory. So let's get started. And so what is the goal? So this is the loose goal of this lecture series. First of all, I want to introduce the space of completed cohomology as defined by Emerton for certain Shimura curves with infinite level at P, with coefficient in a local system which depends on a certain algebraic representation W. And what we are going to see is that the smooth vector of this object are given by the H1, the classical H1 at infinite level with W coefficient. And this is an isomorphism. And second of all, time permitting, I would like to introduce a recent theorem of Breuil, Hu, Herzig, myself, and Benjamin Schrein, and also Hu and Wang, which shows the following fact. So this completed cohomology can be has Ecke action. So if I consider the completed cohomology localized at a certain maximal ideal in the Ecke algebra associated to a modular Galois representation of dimension 2, so here we have R bar, which goes from Gal QP bar F, Gel to F, which satisfies certain technical condition. And F at P is unramified. Then this object carries an action of a local Galois deformation ring. So here I consider the decomposition group has an action of a local Galois deformation ring. And what happens is the following, is that if I consider a map here, X, then the rank of this object is bigger than 1. So this is a recent theorem of Breuil, Herzig, Hu, myself, a Schrein, and Hu and Wang. I will give the exact statement during the course. So let's get started with the real material. So first, in order to state the comparison between completed cohomology and smooth vectors, I need to introduce the basic object. So here we have basic, first paragraph, basic objects and statement of the main theorem. The setup is the following. So I'm going to follow here Carayol, and we consider so F over Q a totally real field. And for simplicity, sorry, for simplicity, we assume that there is only one prime above P. And during this course, we consider E over QP a finite extension, which are the coefficient of our representations. Ring of integer O, residual field F, and we have a uniformizer which I call pi throughout. I consider now a quaternion algebra of center F, and we assume that this quaternion algebra splits exactly at one infinite place. So we have the following situation. F tensor over F with R is isomorphic to a 2x2 matrices times H D minus 1. D is the degree of the extension. D is F over Q. And we consider the reductive group associated to D, G over Q, the reductive given in the usual way. So I consider R is a Q algebra, D tensor over Q, R, and I take the units. Okay, so now it's customary to consider the following object. I consider now K is a compact open subgroup of the finite Adele, which for the remainder of this course, it will be always written as a product. So we have Kp, the Tame level, and K lower p, where K lower p will be a subgroup, compact open subgroup of GZP. Okay, so to this data, we can associate the following object. So the double coset, Y, K, C. I will use this notation. So this by definition is what? So I consider C minus R times the finite Adels mod K, and this is quotient via the diagonal action by GQ. So what is the point? The point is that we assume that the group K is sufficiently small. So the assumption is that if I consider GK, G minus 1 intersection with the stabilizer in GQ of Z, so here G is any element in here, and Z is any element in C minus R. So we assume that this intersection is trivial. So this means that the GQ action over this has no fixed point. And so this means that this YK is a compact Riemann surface. So this implies that this is a compact Riemann surface. And now, something which should be useful later. Whoops. So I use another color now. So now useful later. And why it will be useful later? Because first of all, we consider the cohomology of this compact Riemann surface. But then later on, when we want to put some Galois action on our complete cohomology, it will be important that these objects are actually algebraic over F. So what is useful is that we can actually realize YK over F as a smooth projective curve. So for this reference, there is a summary of this result in the Bourbaki talk of Deligne. So it's a smooth projective curve such that if we consider the complex point, well, the complex points are exactly
Professor, the bottom lines are not visible. Can you just move it?
I'm very sorry. Thank you. Thank you very much. Please.
Yeah, now it is visible.
Thank you.
Yeah.
So if I take the extension of scalars, so this is the unique split place at infinity such that I have M2R. Well, this, and I take the C point, I get what I wrote before. Sorry for this tautology. Okay, very good. So we have a couple of remarks. The first one is the following. So it's possible to prove that, number one, so this is in Carayol and also Deligne, one can see that the connected components of this variety are in bijection with what? With the finite adelic points. Here I quotient out by F, and here I quotient out by the image of K via the reduced norm. So this is the reduced norm. Because in fact, we can write this as a disjoint union of quotient, arithmetic quotient of the upper half space, parametrized by this set. And second point is that if I consider a compact open K prime in K, so this is compact open, then what we get the natural map give us a Galois covering map. So this is the Galois cover. With Galois group, the quotient K over K prime. And this gives us a projective system. So we get a projective system parameterized by compact open in the finite adels. So here I have YKC. And this projective system has an action of the finite adels with a G a infinity action. And this is simply because we have a conjugation. So the conjugation by elements of G A infinity give isomorphism this way. And the nice thing is that all this construction algebraize as well. So this construction algebraize. So this construction algebraize. It will always be the case, and the reference will always be Caraiol and Deligne, based on the work of Shimura. Okay, so now I recall my goal is now to introduce the cohomology space that we are interested in, and to this we want to introduce the local system associated to irreducible algebraic representation of J2. Sorry, of J2. So we consider W is an irreducible. Well, this is not completely, it's not necessary now, but it will be useful to simplify proof later on. So irreducible algebraic representation of GL2 with ecoefficient. So this is a very concrete object. So W is equal to the tensor product over the embedding tau P. So these are the embedding of Fp in E. And here we consider the symmetric power, say k tau minus 2 F P squared times that m tau. So we will never need this explicit description of W, but I simply wanted to spell it out since it will appear very often in the talks during this conference. So this is actually the algebraic representation of highest weight k tau minus 2 plus m tau, comma m tau. Okay, so during this lecture, I will write W naught is a O lattice, which is stable by the action, so J2 stable, and we will often consider quotient, the finite length quotient of this lattice, omega s for some s. So given this data, I can consider the fiber bundle defined as follows. So I consider GQ, and here we have C minus R times the finite adels. But now I consider the product over, well, W naught omega S, and this I quotient on the left by K, where we have the diagonal action of K over these two factors. So meaning what? Meaning that we have, so to the pair X, G, comma V, comma W, sorry, times K, this is by definition. So X is the same, and we have G, K on the left, and here we consider the action of Kp minus 1 times W. So this is how I define this quotient. All right, so these, so we have a vibration of this over the Riemann surface of before, and given this data, so this is, so given this data, we can get a locally constant sheaf, which I called V So this is a locally constant sheaf associated to this representation. So V W naught omega S. So this is a locally constant sheaf. It's the sheaf of section over YKC. Once again, so now what happens? What happens? We can again algebraize all this. So again, we can algebraize the previous construction. And again, this is important for later when we want to put the Galois action. So the remark is the following: algebraization. So if now I consider, so how can I define these sheaves, these locally constant sheaf over the algebraic curves of before? Well, I consider a compact open at P such that the action of Kp is trivial over W naught omega S. So this is exists because here the action is eventually a smooth action. Then we see that W naught omega S defined over K. This is actually so defined over this K prime. So I should remark that this, so to write properly, I should always keep track of the level. So let's write W naught omega SK. I will omit the level during the lecture because it's a bit redundant. And it's not redundant, but it's a little bit heavy for the notation. Okay, so if I take this, well, this is going to be equal to the curve itself times W naught omega S. And recall that here we have, well, here, this is a bundle over YK. And this is a Galois cover. And so, we have that this VW naught omega S for any kind of level K, which is sufficiently small in the previous sense, can be reconstructed as a quotient of this bundle, which I know how to define because this I know how to algebraize. And then I consider the invariance under K over K prime. Recall this is Galois with Galois group K over K prime. And so, once again, this is useful to define algebraically the sheaves. And so we can define, so we set V W naught comma K, by definition, is going to be the inverse limit over S of VW naught omega S comma K, and VW K by definition is just the extension of scalars. Over O. All right, so now we can define the central object of this course, which are the following. So the central okay, so I should apologize because I want to use the black when there is like the ordinary material. So the central object of this course are the following. So I consider what I defined just before. So first of all, I defined HI Y K upper P W naught. So this is defined as the limit over K prime. This is compact open in G. So this compact open subgroup in GQP of HI Y K upper P lower P C V W naught. So I consider this limit. This object for the remainder of this course, for simplicity, will be written as HI K upper P K lower P W naught. And this is also equal to the limit, again, over Kp compact open of GQP of the limit over S of the analogous object, but with torsion coefficient. So here we have K upper P, K lower P, W naught, omega S. All right, so given this, I can now introduce the space of completed cohomology. So we have to consider the following two spaces. So first of all, I have H hat I K upper P W naught. So what is this? Is the p-adic completion. So it's the p-adic completion of this one. So we consider the limit here over S of the HI K upper P W naught over O omega S, endowed with discrete topology. And we have another object which is similarly defined, so H twiddle I Kp W naught. But this time I consider, first of all, I consider the limit over all level of the HI K upper P, K lower P with torsion coefficient, and then I take the inverse limit. So this is S over S. And these are both endowed with the discrete topology. So each of these set is endowed with discrete topology. So at the end of the day, we get a continuous action of GQP. So this is with discrete. And so here we have a continuous action of GQP. This is continuous. The question is now, what is the relation between these two objects? Well, they are related by the Tate module of the cohomology. So first of all, let me say, as for now, we are just considering the simplicial cohomology as the spaces are just compact Riemann surfaces. But then we will see later on that these spaces have much more structure, so they have a Galois action and they also have an Ecke action. Okay, but so I was saying, what are the relations between these two objects? Well, we can consider the following exact sequence of sheaves, so locally constant sheaves. So we have first of all, we have VW naught of level. So the key point is that we want to compare the effect of multiplication by the uniformizer for a fixed level now. So I consider this Kp, K upper P. Here I have the multiplication by pi s, omega s, sorry. Actually, it's a pi. Okay, so pi s. So here we have a W naught K lower P, K upper P. And here we have V, W naught, sorry. By S, comma, K lower P, K upper P. So from this exact sequence, I obtain the following exact sequence of cohomology. So Hi of K upper P, K lower P, W naught, and this is mod omega s. Here I get Hi K upper P, K lower P, W naught omega s inside coefficient. And here I get Hi plus 1 of K upper P, K lower P, W naught. And here I consider the torsion. And so you see that if I take, so if I take now the limit over the inductive limit over all Kp, and then I take the inverse limit over all S, I get the following exact sequence with continuous action of GQP. So now I consider lim over S and lim over the compact open. And I obtain the following. I obtain 0 H hat I Kp W naught. Here we have a closed embedding by construction. Here we have H twiddle. Okay, I actually don't know if it is twiddle or twiddle, but I say twiddle. Okay. And here I have the other complete cohomology. And here I get a Tate module of the usual cohomology in degree I plus 1. So now what happens? It happens that these two spaces here are p-adically complete and separated. And this is p-torsion free. So this is, so these two spaces here are p-adically complete and separated. Because this is a completion, and this is the Tate module. And this is also pi torsion free. This is also pi torsion free. So we conclude that this is also p-adically complete and separated. And so what happens with a continuous action. So this implies the following very important fact, that H tilde I K upper P W naught is p-adically complete and separated. Whoops. Voila. Don't hesitate to tell me if I go out of focus. And separated. with a continuous action of GQP. And so this means that if I pass if I extend the scalars, we get an injection, so a closed embedding of Banach space representation. Here we have H twiddle, KPW. And here we have VP, HI plus 1, K upper P, W. And this is in the category of Banach space representation of GQP with ecoefficient. We are going to see in a second that actually these Banach space representation have very important, satisfy very desirable properties, like being admissible, first of all. So, I mean, of course, I have to define, to recall what is the definition of admissibility. Before that, I can at least state the first main theorem. So, main theorem so this is in the first reference of Emerton. This is a very special case of theorem 0.5. So we have a natural isomorphism. So we have natural isomorphism given as follows. So this is the p-adic completion of our space here. So we have a natural map of HI. Sorry, I'm considering Shimura curve. So I'm considering just the H1. So I consider H1 of K upper P W. We have this natural map to here, to the completion. And then we compose with the closed embedding before. So we have this map. Note that it's false. It's not clear. So it's false that this map in general is injective. But I mean, the key point is the following. In fact, if we consider like the smooth vectors of this representation, well, I get an isomorphism. So it is indeed true that this space can be recovered from the completed cohomology via the natural map. So it is indeed true. And this map is natural in the sense that it is Galois equivariant, is GQP equivariant, and is EK equivariant. So natural, meaning that this is Gal equivariant, is GQP equivariant, and is EK equivariant. Okay. So just out of curiosity, are there any questions so far? Because I'm going to enter the second paragraph, second chapter. So in order to give a proof of this theorem, we need, first of all, the basic notion of local algebraic representation and Banach space representation. In fact, this space can be also described as so this space can be also described as the following, as I consider the representation with trivial coefficient and I tensor up with W, and I take the smooth vectors. So these are the W locally algebraic vectors of this space. All right. So part 2, locally algebraic and Banach space representation. Locally algebraic and Banach space representation. Of GQP. All right. So the first lemma is gives a characterization of locally algebraic representation, local algebraic vectors in a representation with E coefficient. So we have the following lemma. So we assume that W over E is an irreducible algebraic representation of GQP, and we consider V over E any GQP representation. Then what happens? Well, I can consider the following object. I can consider, so let's see. I can consider the limit over all level KP. These are, as usual, these are compact open of the maximal compact of GQP. I consider the KP equivariant homomorphism of W V. I tensor up over E with W, and I consider V. So this is the evaluation map. So this map is injective. The image of this map is what we call the W local algebraic vectors of V. So this object here will be denoted in the following, will be denoted as the H0 stable. So with respect to, so this is not important, but let me write as well, GCP of what? Of V times W dual. Well, the fact that here we use this is clear because this home space is in fact the space of KP invariant of V tensor W dual. So this is, we will see later that this object, so these are the smooth vectors of V tensor W dual. We will see very soon that this functor can be derived. And it will be crucial to understand the behavior of smooth vectors in the completed cohomology. So what I want to say is that this map is injective. So I give a sketch of the proof. So it's enough to show that this map is injective for a fixed level. So it's enough to show at finite level. KP. So now we have the following. We have that W dual times W. So this is isomorphic to the endomorphism as E vector space of W dual. And actually, this map is injective into what? Into the space of functions. So this is injective in the space of function over Kp. Dual. And this map is injective because we are assuming that they represent, whoops. Now you can see?
Yes, we can see now.
Oh, what is the algebraic representation of GQP? No, okay, right. It's an algebraic representation of G over QP. Thank you. Thank you. So we have this map which comes from the fact that here EKP surjects in end EW by irreducibility. So we have this surjection and then we dualize. And here we have the evaluation at 1. Okay, so now we tensor with V, and what do we get? Well, we get the following. So this, so we get that V times W check times W injects in V times the space of function. So sorry. These are the function of from Kp to E. And here we have the evaluation map V times E. So we get this, and now we pick, and now we take the invariant. And so take the invariant by the following. K goes to K, K, 1. So if I take the invariant of this first term of by K, K, 1, so you see that I get exactly, I get exactly this term here without the lemma. And if I take the invariant over here, well, these the invariants here will become just E. Okay. So what is the corollary? Well, the corollary is that if I now consider all possible irreducible algebraic representation, well, the image in V, they cannot interact. So the corollary is the following. If I take now the direct sum over all algebraic representation, irreducible, so this is irreducible algebraic representation, so I take the stable H0 stable of V times W check, and here I tensor with B, we have an injective map given by the previous, so this is, say, call this evaluation at W. Okay, I take this direct sum, and this map is injected in here. So now we can define the locally algebraic vector L-alg of V. They are defined as the image of this direct sum of EW. And this is a GQP representation. Is a GQP representation. Okay, so what is the upshot? The upshot is that the main theorem can be restated as follows. So upshot. The main theorem is now the following. So I take the direct sum over all irreducible algebraic representation of G2 over E. I take the H1, the usual H1 with infinite level at P coefficient in W. I tensor up with W check over E. Well, this is exactly the space of locally algebraic vectors of the completed cohomology. With trivial coefficient. So locally algebraic. And this is natural in the sense that it is GQP. We will see later also is Galois equivariant. And is Ecke equivariant. Okay, as I mentioned before, a key point in order to prove this isomorphism is to understand the property of this representation as a Banach space representation. So the theory of Banach space representation of p-adic group was developed in the early 2000 by Schneider and Deiterkamp.
Side, the degree of the cohomology is 1 and the right hand side is I. So is it on one of those? Yes.
Hopla. Thank you very much. Yeah, absolutely. Thank you. Okay, so now we want to understand the basic notion of Banach space representation. So let we fix a compact p-adic analytic group. So let H be a compact p-adic analytic group. Given this object, we can consider the completed group algebra, denoted as O double bracket H, which is by definition the inverse limit over H prime compact open normal of O H mod H prime. So this is a compact topological ring which is p-adically complete. So compact topological ring which is p-adically complete. Okay, and the main theorem of Lazare in his IISER paper of the 60s is that this ring is actually Noetherian. So the theorem is that we have an injective map of the group ring in O double bracket H, which has dense image with dense image, and the ring OH is Noetherian, non-commutative but Noetherian, and OH is Noetherian. All right. So what is the basic example? Whoops. Sorry, I just need to make sure. So I think I still have a short time. I would like to give some example of some properties. So the basic example is the following. is that if H is just ZP, then O double bracket ZP is isomorphic to OX, sending the class of 0, -1 is sent to X, sorry, opla. And this is with the X var pi adic topology. Okay. And so what is the lemma and the definition? So we have the following lemma. So this lemma is in Schneider-Teitelbaum, the reference. So this is in Schneider-Teitelbaum, is that if V is a Banach space representation with E coefficient, so it means that V is a Banach space over E with a continuous action of H, then the continuous dual, so V check defined as Hom continuous over E of V, comma E, is a module over the completed group algebra. And so what happens, so I'm going to skip the proof of this, and I would like to get right to the point. So the definition, Schneider-Teitelbaum, is that V is admissible if the dual is finitely generated over what? So in fact, this is a module over here. I have to invert P. If it is finitely generated over OH, where I invert P, this is equivalent to the fact that there is a lattice, such that the mod P reduction is an admissible smooth representation with FP coefficient in the usual sense. And so the other basic example is the following, is that if I consider V by definition is the space of continuous function HE, so the continuous function with the subnorm map and the right translation by element of H, so this is admissible because the dual is exactly the ring here. Because also the situation is that we have the smooth function HE, this is dense in V, and so this means that if I dualize, V check is injective in, well, I take the inverse limit. So these smooth functions are the direct limit. These smooth functions are the direct limit over H prime of the continuous function of the finite quotient in E. So when I dualize, you see that this injects into the inverse limit. So this is injects into OH times E, and this actually, we can see that this guy also contains OH times the evaluation at 1. And so we get that, V dual is actually isomorphic to OH 1 over P. So the key theorem, again of Schneider-Teitelbaum, is that this functor, V goes to V check, induce an equivalence of categories. So the category of admissible Banach space representation of H is equivalent to the category of modulus of finite type over this algebra. And so in particular is abelian. So this is an equivalence. So in particular, the category of Banach space representation is abelian. And the functor respect short exact sequences. So I finish on the following statement. So, sorry. Okay, all right. Sorry, I have a gigantic amount of paper here. So I finish on the main theorem, a final statement for the main theorem. So this is Hamilton 1, theorem 215 and 211. So first of all, H tilde Kp W is a Banach space representation, which is admissible. So this is Banach admissible, say GZP. And actually the action is unitary if, moreover, VW is the trivial representation. So, meaning that there is an invariant lattice in here by the action. So with unitary action, if W is equal to E. And second point is that we have a factorization as follows. So H1, as I mentioned to you before, is the usual thing that we saw already a few times. So we have H1 is the natural map with dense image. Here we have H1 hat K upper P W. Here we have the closed image, closed embedding here, H tilde 1 K upper P W. Here we have the smooth vectors. Smooth. And so we have a factorization here with an isomorphism. And this is in fact, this map here is in fact the edge map of a spectral sequence. So edge of the following spectral sequence: Hi stable, GZP, H tilde J, K upper PW. This converges to Hi plus J, K upper PW. In particular, we will see that it makes sense to derive these functors in order to make sense of this object. Okay, I think now I finish my time, and this is like the first course for us for today.
Thank you very much, Professor Morra. Any questions?
Thank you.
It's 1:30, I think, in Indian time, so people are hungry. Okay, maybe we can have questions in the later lectures. Let's thank Professor Morra. Thank you very much, and see you soon.
Thank you. It's my pleasure.
Thank you. So we will meet again at 2:30. Okay. Thank you.